Welcome! Let's dive into nanomedicine, where the nanoscale in our body intersects with medical technologies for better healthcare. Why do you think size matters in our health? Look at ourselves. We rely on our senses to guide our activities, much like how roads and traffic systems help us navigate safely. Similarly, at a smaller scale, cells and biomolecules use complex mechanisms to function, like obtaining nutrients, communicating with other cells, and traveling within tissues in the body. We are literally just a giant collection of cells and molecules that are millions of times smaller than us. Though we think we behave freely, we simply function based on what our cells and molecules collectively tell us to do. Take the skeletal system as an example. At a glance, it provides structure to our body and protects our internal organs. Here is the junction of the axial and appendicular skeletons, showing bones like the lower back, lumbar vertebrae, the hips, pelvic girdle, and the legs, femoral head, femur. When you zoom in, say to a long bone, you'll see a porous region called spongy bone, a dense region called compact bone, and a hollow region filled with bone marrow where stem cells reside. Zooming in further to the microscale, you'll observe various structures, textures, and organizations of the bone. There are bone layers like lamellae and gaps like lacunae throughout the spongy bone, allowing bone cells such as osteocytes, osteoblasts, and endothelial cells along blood vessels to reside. These bony structures outside the cells, called the extracellular matrix, contain organic materials like collagen, non-collagenous protein sugar molecules called proteoglycans, integrin-binding ligands, and calcium minerals like hydroxyapatite. At the nanoscale, the arms and feet of the cells, such as integrin receptors, bind to the extracellular matrix for grip. Just like our roads and traffic facilities, these nano and micro-sized highways are used by the cells and tissues to carry out their daily activities, such as healing wear and tear from our development, aging, fractures, or broken bones. It's quiz time. Stuck? No worries. Pause the video, check back on the previous slides, or feel free to Google it. Let's dive into nanomedicine, miniature, biocompatible, and functional, where small solutions solve big challenges. Miniaturization is the foundation of nanomedicine. For context, 1 nanometer is 1 billionth of a meter, or 10 to the power of -9. However, for a product to be marketed as nanomaterials, international agencies like the International Organization for Standardization, ISO, and the European Commission specify that the design of materials or devices must include dimensions at the nanometer scale, typically 100 nanometers or smaller. At this incredibly small scale, materials exhibit unique physical and chemical properties. For example, gold nanoparticles change color depending on their size, a feature that has revolutionized diagnostics. What makes miniaturization so powerful is that nanomaterials are comparable in size to biological structures. For instance, DNA is about 2 nanometers in diameter. Proteins range from 1 to 10 nanometers, and cell membranes are approximately 5 to 10 nanometers thick. By maintaining dimensions below 100 nanometers, nanoproducts achieve precise interactions with cells and biomolecules, opening the door to applications once thought impossible. It's quiz time. Stuck? No worries. Pause the video, check back on the previous slides, or feel free to Google it. For nanomaterials to be used safely inside the body, they must be biocompatible. This means they need to interact with living tissues without causing harm. No inflammation, no toxicity, and no immune rejection. Biocompatibility is often achieved by designing features that closely mimic the structure, scale, and environment of the target tissue. Although compromises must be made to reconcile ideal designs with the practical realities of production, business priorities, and patient affordability, thoughtful engineering still aims to achieve the safest and most effective outcomes possible. It's quiz time. When a material is not naturally suited for medical use, surface modification improves its functionalization and performance at the micro and nanoscale. We can achieve this chemically by adding functional groups or switchable chemistries, biologically by coating surfaces with proteins, peptides, or antibodies, and biophysically by engineering surface patterns or tuning biomolecule conformations. These modifications help nanomaterials target specific tissues, respond more precisely to biological signals, and improve treatment outcomes. It's quiz time. In this module, we explored how scaling down to the nanoscale improves precision in healthcare. Nanomedicine typically involves miniaturization, biocompatibility, and functionalization, with real-world applications like clear blue, trabecular metal, and doxil. Thank you. See you in the next module.